where does one even begin to learn how to approach this problem?
Like designing hardware or designing
Yeah,
an
yeah,
FPGA?
well, I both of these, right? I this is an area that I've not even considered looking at. I don't know what resources are available. I don't know where you even begin.
Yeah, so since a lot of this information is kind of just esoteric, because hardware usually is that way, um, I was kind of like, well, I can't really find good. Well, I did find a blog post that kind of was like, here is how to design an FPGA in quotes, but using just big IC chips. So like a big dip chip on breadboards, and I was
Mhm.
like, cool. Now I kind of have to translate that into Dart code,
Mhm.
which then gets translated over into Verilog.
Mhm.
And so that's kind of what I was able to do. I had Claude help me a little bit there, but like I still was following the same principles. Everything was like, you know, the way the industry does it, which is the normal grid-based LUT4 kind of style silicon.
Mhm. So, okay, you have this thing that takes an entire data build. Where do you go from there? You've designed the FPGA. What happens now?
Now, so right now I'm doing a little bit of like the last stage
Mhm.
before I get this chip manufactured, which is like all the verification stuff, making sure like everything works.
Mhm.
So I'm throwing into something called I'm converting it over to a format called Spice,
Mhm.
which is a netlist format. Netlists are complicated. They are a way of basically describing circuits.
Mhm. Mhm.
And Spice is a common one that's existed for forever now, and you just throw your Spice file into a Spice simulator, and you're simulating hardware then. And so I'm working on trying to verify, will this chip work, or will it just completely break itself if I throw it over to being manufactured?
Mhm.
But once I do know it is actually going to work, which I am finding that out pretty soon here. It just takes forever to iterate because it takes literally an entire day, an entire 16 to 24 hours to just process all this stuff.
Right. So, like a typical software example would be, let's say you are developing the Linux kernel and you're building the entire thing on a netbook. And every time you want to check a change, you've got to recompile the entire kernel.
Yes, but this is more extreme because I'm doing this on, an 128 core Ampere Ultra desktop with half a terabyte of RAM. And
Okay, so it's like, right. So it's a powerful machine. This takes forever.
yeah, even on like if you try to do this, not on an ARM system, like if you try doing this on like a Ryzen or a Threadripper or Epic or literally
Mhm.
anything,
Mhm.
you are waiting at least 6 hours. And like from what I can gather, like bigger designs, like my design is quite small in comparison to the rest of the industry. If you have something that's like on the scale of like Xilinx, which is the biggest FPGA company,
Mhm.
they're probably spending a few months just getting this processed, and it's probably done on a cluster.
Mhm. Mhm.
So many times more compute than my single desktop here, and they're still waiting a insane amount of time because these are NP hard problems. You have the door-to-door salesman problem of just find or like the neighbor finding problem where it's like you can't find where to put the thing because the next thing needs to know where the other things are at.
For anyone who's, maybe we should, for anyone who might not be software engineer background or tech background, NP hard. Just brief overview of that because we've used that term a few times. Maybe this, I just realized trying to explain what NP hard is actually is a relatively annoying thing to do as well.
Yeah, NP hard is hard to describe. What was it? Like N and P represent two statistical things in computer science. I don't remember what they are. There has been a ton of like academia behind this over the past probably 50 years now. So I recommend anyone who doesn't understand it, just please look into that if you really want to dig into this. And
TLDR, it's really, really difficult. That's what you need to know, I guess.
Yeah, it is, like what I was saying, the door-to-door salesman problem, just like finding where is the most available space. And so you can't find available space until you start putting stuff down, which means this is doing thousands of iterations, which each iteration takes probably 10 to 20 minutes, and so it just gets exponentially longer as you scale up.
So, as you're doing this testing, what are the kind of things you're looking for that can go wrong?
So the very low-hanging fruit ones are DRC failures, so DRC being design rule checks. So that's stuff like, oh no, you're shoving 5 volts two 5-volt signals against each other, and now you have magic smoke. That is a very easy one. Other ones is like, oh no, this trace is 2 microns not wide enough. Just need to make this trace a little bit thicker.
Oh, okay, yeah, right, okay. I'm guessing if the trace is too thin, then the signal is not able to pass through it correctly?
More like, you know how there's different, like, gauges of wire? It's kinda like that, but instead of being, like, millimeter or centimeters wide, this is microns wide, or
Right,
even
okay.
sometimes nanometers wide.
Okay, so if it's too thin, you could burn the trace and then basically kill it.
Yeah, you
Okay.
don't wanna you don't wanna send too much power down a thin trace, or you are going to have problems.
Okay, that makes sense. What are some of the more, I guess, complicated problems you can find?
Um, More like the antenna problem, which is as you have noise, or rather, as you have signaling going through a chip, that creates a bit of electromagnetic interference that you try to clock things higher, which then naturally, uh, energy wants to kind of just go wherever, and if you have enough of it, it'll emit enough that you can then pick up the electromagnetic interference and then get a wireless signal, which then by definition is an antenna. So, like, I have a piece of wire here. By definition, this is an antenna. Yeah. So there is a lot of fancy math that happens, and it checks to see whether or not you've not accidentally created an antenna.
Right, so you could accidentally have... you could have electronic interference jumping between traces rather than just following where it's supposed to
Traces,
go.
traces, different layers. Sometimes it's trying to get the stuff to actually use the right routing so that it doesn't accidentally create an antenna. And then just like there is at least a command that happens that the tooling provides that just repairs antennas. It's literally called repair antennas, and it goes through and it's like, if this is an antenna, it's no longer an antenna. There's a
Oh.
lot of math of how it figures that out. It gets very complicated. People have made this happen, and it makes it not a problem.
Mhm. Okay, I guess that makes your life considerably easier.
Yes, it can.
Okay.
But because you're still dealing with physics, sometimes it's not always going to be accurate. So you take it with a grain of salt and hope by the time you actually get the chip manufactured and start using it, that you don't have any accidental antennas created.
From manufacturing faults or from the math not fully catching everything?
Both.
Hmm.
Because since the CMOS like lithographing process isn't always perfect, it never will be perfect. You'll always have some amount of yields that are bad, some yields are good. This is known as the silicon lottery
Hmm.
that
Hmm.
everyone plays a game with when you use silicon.